Thank you. So, ladies and gentlemen, can you all hear me from the back? Yeah. And if my voice fades, start waving. I'm extremely honored to be giving this lecture, and I hope you haven't been too put off by the introduction and that your expectations are not too high. So this is the title of my lecture, which I'm not going to read out because I don't speak Welsh. But you can, and if you haven't gathered, I'm from University of Nottingham, where Robin Hood used to live. And, well, he lived north of Nottingham. And so the point of my lecture, or the aim, is to show how I became fascinated by supercritical fluids. I'll explain what those are, and how they led me to green chemistry and engineering. And the real point I want to make is the role of chance events in making this happen. So this year, many of you may know, is the International Year of the Periodic Table, because 1869 was Mendeleev's first publication of his periodic table. Other people also proposed quite similar things, but Mendeleev was more successful in promoting it. Some say because he had funny hair, and also because he made predictions. But people are much less familiar that in 1869 was the year of the so-called Bakerin Lecture by Thomas Andrews, who was professor at Queen's University, Belfast, and he defined the so-called critical point. And there's rather a nice picture of his apparatus in his paper that was published in 1869. I should say, because of one has to be accurate in engineering, he didn't actually deliver the lecture, but you can see it says received in June. It was just before the summer holidays, and the Royal Society realized, my God, nobody has given the Bakerin Lecture this year. And this paper arrived, and it was declared the Bakerin Lecture. And apparently Andrews was quite disappointed he didn't give a lecture, so he gave it 4 years later. Anyway, outside my office is this photograph, which is of Andrews's first three-dimensional phase diagram of CO2. It looks quite artistic, but you can't really understand much from it from a picture. Has sort of temperature, pressure, volume. And it's easier perhaps to look at a two-dimensional phase diagram, which is what people normally use to explain what a supercritical fluid is. And so you have temperature here, pressure there, solid down here, liquid there, gas there. And the critical point is the end of the line between the gas and the liquid. And if you haven't seen it before, it's really quite fun to watch what happens if you heat up a cell containing gas and a liquid. So here is a cell with the liquid down here and the vapor above it. So let me just try and show you what happens when you heat it. When you start heating it, it begins to boil. Material goes from the liquid phase to the gas phase, and because it's sealed, the pressure goes up, so the gas gets denser. The liquid expands as your heating gets less dense, and the line disappears between them. And then it's even more fun when you cool it down again, because then it separates with this sort of storm. And I used to keep the apparatus for this in my office. And when somebody came and said they were interested in doing research with me, I would show them this. And if they went, wow, I knew they were suitable. If they looked bored, I suggested they went to go and see Professor X or Y down the corridor. So there's also a very important paper published 11 years later by the Scottish scientists Hannay and Hogarth, who published a paper with a fantastic title on the solubility of solids in gases. And they demonstrated that although a supercritical fluid is just a compressed gas, you can dissolve solids in it. And this is their picture of the apparatus from their paper. It's not as beautiful as Andrews's drawing. And the solubility of things in CO2 is used commercially, particularly for decaffeinating coffee. Well, coffee beans before they've been roasted. And the traditional way of decaffeinating coffee beans is with dry cleaning fluid, which, as you can imagine, leaves interesting residues in the coffee beans. But CO2 is completely non-toxic. Caffeine is soluble in CO2, and you can extract the caffeine from coffee beans. If you haven't seen it before, this white thing here is about the amount of caffeine from 300 cups of coffee. Of English coffee, it's probably about 100 cups of Italian coffee. And it should be pure white, but this was extracted by undergraduates rather than supercritical fluids, so it's a bit brown. And so this is now done, extraction with CO2 decaffeination on a big scale. This is serious engineering. Here is a extraction vessel for decaffeination of coffee and coffee beans, and you can see there's some little workers down here for a scale. And the process itself is quite nice. You have a big column, you feed the beans in at the top and they come out the bottom, and the CO2 is circulated around. The coffee beans have to be kept wet, otherwise the process doesn't work. And so the caffeine, it comes out here, and you could just expand the CO2 and the caffeine would come out. But that's quite expensive in energy terms, so it's washed out with water. Caffeine's more soluble in water than CO2, and you drain off the solution here, and this keeps the CO2 wet when it circulates. And of course, it's a brilliant process because the beans come out more valuable than when you put them in. And you have the bonus of the caffeine, which you can sell to Coca-Cola to put in their drinks. So you've increased the value of your beans. So that's the end of my introduction. So now let me begin my own story, which begins in 1984. When I was, at that stage, an inorganic chemist looking at chemistry of metals like manganese, chromium, and so on. And in particular, my research interest was detecting really short-lived molecules at low temperatures using infrared spectroscopy. And infrared light is absorbed by the vibrations of atoms in molecules. And if you're studying something dissolved in a solvent, you don't want the solvent to absorb the infrared light, or you won't see what's dissolved. So solvents, we were using liquefied noble gases, argon, krypton, xenon, which only have one atom in the molecule, so they can't vibrate. And so they're completely transparent in the infrared. But they have one problem, that these three gases have very limited liquid range. Between the melting point and the boiling point, it's only about 4 degrees centigrade. But if you increase the pressure up to 20 atmospheres, they extend the liquid range and they overlap. That the molecules we were making that were meant to be unstable were actually less unstable than we expected, and we needed to warm them to higher temperature and to go to higher pressures. And so I was stuck. And then came the first chance event. In November 1964, the airline TWA, Trans World Airlines, which has now gone bust, had a special offer. If you flew to the United States, you could have 8 internal flights anywhere in the United States for $25 per flight. And I went to the States with one of my students, Barry Moore, and he was determined to use all 8 flights. So he made a side trip to visit a physical chemist, Veronica Weider, in Boulder, Colorado. This was, I don't know, 2,000-mile detour for $25. Well, $50 because he came back. But the key thing was that he saw that she had a high-pressure cell with windows, and he invited her to visit Nottingham and bring the cell. So just after Christmas, Veronica Weider came to Nottingham, brought the cell, which you can see here, and left it behind. So then my research group had the high-pressure cell we needed. And of course, the first thing we wanted to do was to try and demonstrate that solids will dissolve in supercritical fluids, these highly compressed gases. And I remembered from being an undergraduate that there was an intensely blue compound that I'd used in the organic chemistry lab called guaiazulene. So we decided to dissolve up guaiazulene. So this is the molecular structure of guaiazulene. And these are some pictures of a demonstration lecture, the demonstration we did afterwards, but of the same experiment, where you can see the guaiazulene dissolved in liquid with a gas above it. And as you heat it up, the meniscus goes flat and then disappears, but the guaiazulene does not precipitate. You could, of course, ask, why doesn't the whole tube go blue? Well, if you're a chemical engineer, you'll say, well, it's a narrow tube and you would get very bad mixing. But I fell in love with this stage. And I had a new PhD student, Steve Howdell, and here he is working with a high-pressure cell with the infrared spectrometer. Steve is now my head of department, so he's my boss. And we did some experiments using hydrogen. And the reason why we were using supercritical fluids is that hydrogen is not very soluble in ordinary liquids. You have to stir very hard to overcome the mass transfer across the phase boundary. But a supercritical fluid is a gas. Hydrogen is a gas, so they mix completely. And so you get much higher concentration of hydrogen in the supercritical fluid for a given pressure of hydrogen than you do in an ordinary solvent. This slide was originally made for primary school children, so you can see blue plus yellow makes green, just to demonstrate that they mix. And so we first had this idea in the late 1980s, and one of the things we did, we made the first compound between hydrogen and manganese, this compound here, which is completely useless but was quite exciting for me because chemists like to make new molecules. But there was a problem. Steve is very big, bigger than me, and has rather strong hands when working with equipment, and he managed to break 2 of the very expensive infrared windows. This is a 50p piece just as a scale of how big this window was. This is sapphire. And he managed to break 2 windows in one morning, which cost the entire budget for his year's PhD was lost in the morning. And so it became clear to me that we needed more funding if we were going to go on with supercritical fluids. And then came the second chance event. My professor, Jim Turner, wanted to do some really quite exciting experiments that needed quite a lot of money. So he invited Don Braben, who at that time was director of the BP Venture Research Fund, to come to lunch in Nottingham with the hope of getting money out of him. So Jim did his pitch over lunch, and I can't remember exactly what he said, but he ended up with the sentence, it's really quite adventurous, I'm not sure if it will work. And Don Braben smiled and said, well, that's why it's not venture research. And I became furious. You see, my hero, the professor, had been insulted. So I rushed in, I mean, metaphorically, into the discussion and made a passionate explanation of what supercritical fluids were and why they were so interesting. And Don Braben said, that sounds very interesting, write me a short outline proposal. And the upshot was, here is Don Braben, I got a grant called Supercritical Fluids and Environment for Reaction Chemistry, which at that time was the biggest grant that any individual had got in the chemistry department at Nottingham. And Don Braben, who's still alive, but they closed down his venture research unit shortly after I got the grant. He did not believe in peer review, which he thought stifled innovation. So, though he denies this, he gave money to people that he liked and found interesting, without any peer review, and I was just fortunate that he found me interesting. So once we got this money, I had to decide what to do, because it was just a very short proposal that we'd written. And one of the things that chemists are meant to do is to make new molecules, or isolate new molecules. And I'm a very bad synthetic chemist. And I'd never made a new molecule in a large enough quantity to see. So I thought this was my opportunity. And I had a very close German friend, Friedrich Gravels, who's now sadly passed away, who's a brilliant synthetic chemist, but who had not been able to isolate compounds of chromium and ethylene. And the problem is that you can make these compounds in solution, but as soon as you try and evaporate the solvent, the ethene comes off and the compound decomposes. You sort of lose the baby with the bathwater, if you like. And my idea was that if you did this reaction in very high pressure ethene, then if the ethene came off, it would go back on again, or another one would go on again. And if you suddenly expanded the solution very quickly, the molecules would be in solution, and suddenly they'd find themselves in the solid state without realizing what had happened. And once they're solid, they're locked in a crystal structure and they're stable. So the idea was you would have a pump, a cell where you could irradiate with UV light to promote the reaction, then an infrared cell to monitor the reaction and release the pressure and get the product. So that's the theory. Here's the apparatus, the pump. You dissolve up the reactant there, irradiate with UV light, and monitor by infrared, and the product comes out here after expansion of the fluid. This is an engineer's approach to synthetic chemistry. You turn a handle and the product comes out. And it worked. And here is the hand of my student James Bannister holding a sample of a chromium carbonyl ethene complex that Friedrich couldn't make. It wasn't completely pure, but it was 80% pure, and I felt I had been vindicated. But then, this was in the early 1990s. At the same time, green chemistry was invented in the United States. Green chemistry, as was mentioned in the introduction, is a cleaner approach to making chemicals and materials. And the idea of green chemistry is that you do something in the lab and then get it into industry on a large scale. And one of the directions that was promoted in green chemistry were cleaner solvents, and I was working with supercritical fluids, supercritical CO2, so it was a good opportunity to get into a new area. And even better, the EPSSC and the Royal Academy of Engineering advertised clean technology fellowships, 5 years doing research with no teaching. And I was lucky enough to be awarded one of the first of these 5-year fellowships. I did actually do some teaching as well, but don't tell the EPSRC. And then the next chance event happened, and there was an article in New Scientist about supercritical fluids, which had the title, "Solvents Get the Big Squeeze," because you were compressing. And I was rather disappointed by this article. I felt it hadn't done my research true, given it to sort of the justified, well, the treatment it deserved. But there was one piece or quote from me which talked about vending machine chemistry. It didn't have this picture, by the way. And I was quoted as saying that the chemist will simply press a button and the machine will add the appropriate reagents to the supercritical CO2 and pump the mixture into the reactor. And so the article was published. Nothing much happened except I got a bit irritated. And then about 2 months later, quite late, sort of 9:30 in the evening, I got a telephone call at home. And it was from this gentleman here, Tom Swan, who at that time was CEO of the second largest privately owned chemical company in the UK. And he said he had read about this vending machine chemistry and he wanted to work with me to make it reality. And after a bit of discussion, well, several months discussion, we decided that what we would do is to do so-called hydrogenation, adding hydrogen to organic compounds. And I apologize to the chemical engineers here that this apparatus is really quite simple. You mix the substrate, the stuff you want to react, and hydrogen and supercritical CO2 with a mixer. Eventually, we used a bed of sand rather than a propeller, but to begin with, it was a mechanical one. It goes through a reactor with a catalyst. Reactant turns to product. Here, you release the pressure, and the product goes one way, and the CO2 as a gas goes the other way, and you can recycle it. So that was the theory. And here it is in the lab with the mixer there, the reactor here, which is about, I forgot to bring a reactor, it's about 5 centimeters long. And the product then comes out the bottom. This is my then postdoc Pete Licence, who's now also a professor at Nottingham and director of our carbon neutral lab. And this worked really well, so working with Thomas Swan, we scaled it up to 1,000 tons a year reactor, plant. And you can see here's the reactor with a worker as a scale bar. And you can, this was a continuous plant, and it worked really well. And opened on July 2002, and the product came out absolutely pure, apart from a slight bubbling like flat champagne, and you could sell it without any purification or anything else. The problem was that shortly after the plant opened, the price of energy suddenly rushed up, and compressing the CO2 became too expensive for the economics of the plant. So sadly now it is closed and is not, and disappeared. But I'm pleased to say that 17 years on, we're still working with Thomas Swan, but on a different project. So after this, we went on to make automated reactors. Because if you have a continuous reactor and you have to take samples all the time to see how the reaction is going, even I, as an enthusiastic professor, have to say it's a bit boring. So we came up with the idea of putting in an automated valve that would take samples every so often and send it to a chromatograph for analysis, and the analysis would be stored with a computer. I apologize, this is rather an old slide, so you can see there's a rather vintage computer there. And what this means is the apparatus by itself can go through a whole series of reaction conditions, temperature, pressure, flow rate, and so on, while the students are doing other things. In the days before the internet, I was at in an airport with one of my students who said, I must find a computer, I want to see how my experiment is getting on. And so it really enables us to increase productivity a lot. And just to give you an example, this is the sort of output. You may not be able to see it at the back. You get percentage compositions here as you change the temperature of the reactor. And this is with a material called furfural reacting with hydrogen. Furfural is a byproduct of processing cereals. And you can see at low temperature nothing happens, and with this copper chromite catalyst, as the temperature goes up, you first of all get this red product, furfural alcohol, being made. If you go to high temperatures, you can get a completely different product, methyl furan. And so you have rather an interesting situation of a catalyst, which if it's warm gives you one product, and if it's really hot gives you another one. And having found out this reaction, it opened up the possibility of making our chemical vending machine a reality. Because if you think about it, if you have a catalyst, a reactor, or two reactors in series, you can either have this one warm, or that one warm, or you can have one switched off and the other one on. And so there are three possibilities. If you put in our catalyst, which works at two different temperatures, then you get 5 different possibilities. And so my student Jamie Stevens, starting from this furfural, had different combinations of reactors. Black means it's really hot, white means it's medium temperature, colorless means it's not on. And just by switching the temperatures with a computer, you could make 5 different products and choose which one to come out and switch backwards and forwards between them. And the yields, a couple of them are only 80%, but the other ones are all over 90, nearly 100% yield, which for chemists is pretty good. And that brings me on to my last chance event, in which I met my colleague, Mike George, in the corridor at Nottingham. And he claims it was on the 1st of April. I can't remember the date, but it was in 2004. And he said to me, we're going to make anti-malarial drugs together. And I was a bit surprised, but he persuaded me. And the reason that he was interested in making anti-malarial drugs is because of a property of oxygen. So, unfortunately, the person who introduced me, the professor, gave up chemistry at A levels, so you need a little explanation or you won't understand the next bit. The oxygen that we're all breathing is really unusual because it has 2 unpaired electrons. Most molecules have all their electrons paired up, but it's so called triplet oxygen. But if you have a dye which absorbs visible light and shine light on it, the dye can transfer its energy that it's absorbed to oxygen and make these 2 electrons pair up. And this oxygen with a paired electron, so-called singlet oxygen, is far more reactive and can be used for making all sorts of things, including anti-malarial drugs. So this, of course, was well known. But what Mike had realized is that the explanation I told you about hydrogen in supercritical fluids applies equally well to oxygen in supercritical fluids. Oxygen in supercritical CO2 will give you a very high concentration, and the advantage also is that supercritical CO2 doesn't burn. I haven't checked where the fire extinguishers are here, but I'm sure somewhere in here there will be a fire extinguisher with CO2. So the problem normally when you do reactions with an organic solvent, which is basically petrol and oxygen, is that your experiment is halfway to having an explosion. So if you have supercritical CO2, it will remove a lot of the problems. And so the reaction we decided to try was a very well-known reaction of this singlet oxygen of this molecule called alpha-terpenine that can react with oxygen in the presence of light to make ascaridole. Ascaridole is an old-fashioned treatment for intestinal worms, and was discovered by this reaction by a German professor called Otto Schenk in the late 1940s. And you can get this dye here, which has the unromantic name of TPFPP, which is soluble in CO2, and the argument is it's non-flammable. Doing the reaction in CO2, CO2 is non-flammable. You have easy separation of the product, you just expand it, and it's miscible with gaseous oxygen. So the first experiment we did was in this little cell here. This is my then postdoc Rich Bourne, who's now at the University of Leeds. And we produced in this little cell 30 microliters of product. You can see here's the product with the 2p piece for scale. I don't know, do you have 2p pieces in Wales? So you can see. And, well, you must do, don't you, because it's got the Prince of Wales' feathers on it. And then we wanted to scale up the reaction, but you can't easily scale up high-pressure reactions because big high-pressure vessels are very expensive. So we built a continuous flow system and scaled up the reaction by 3,000 times, going from 30 microliters up to 96 milliliters. Ascaridole is colorless, but this looks a reddish color because it contains the dye. And since then, this is our original flow reactor. We flowed the oxygen CO2 through it. This is our more modern one. And for the light source, it uses LEDs. Everybody knows what LEDs are now. They're the things you have on your iPhone, except that these are much more powerful ones. The original ones we bought were the sort that were used in Audi cars, but you could buy the LEDs without the car. And so you can see we've published lots of papers on this since. So you'll be asking, what about antimalarial drugs? And the main antimalarial drug is called Artemisinin. It's got this strange name because it comes from a plant called Artemisia annua. And the traditional way of making Artemisinin is by planting Artemisia, harvesting it and extracting it, and you get out Artemisinin. But even in the best conditions, in subtropical climates such as southern China or Vietnam, this takes months to do. And the supply of Artemisinin is never quite enough for what is needed to treat people. And chemists can make anything. So they can synthesize Artemisinin, but not at an affordable price to compete with the agricultural Artemisinin. But then it's been cut off at the bottom. The company Sanofi started a process which is called a semi-synthetic process, where you take sugar and genetically modified yeast and do fermentation, and this produces one of the intermediates, artemisinic acid, on the way to artemisinin, and then you do chemistry, including singlet oxygen, to make the artemisinin. And here's their pilot plant in France, and they use dichloromethane, which is not a particularly desirable solvent. And if you look at the whole thing from a green chemistry point of view, they use photochemistry and singlet oxygen, which is really very green, but they use dichloromethane as the solvent. They use trifluoroacetic acid that's really toxic, and they don't recycle the photocatalyst, and they need other solvents to purify it. And it's done in a batch process, in a large vessel, which is not very good from the point of view of photochemistry. So the German chemist Peter Seeberger did a continuous process. You can see his apparatus is quite complicated, and he managed to change to toluene, which, although it's not a particularly good solvent, is, non-toxic solvent, is less problematic than dichloromethane. And he managed, at least in his first papers, to get about 46% yield. So we decided we would try this in supercritical CO2. It's our student Jess Bellamy and postdocs Zach Amara and Raf Horvath. And the reaction is in two stages. The first part has light and singlet oxygen. The second part has acid and uses ordinary oxygen with the unpaired electrons. And we had the idea of combining the acid catalyst and the photocatalyst into a single combined catalyst. So you take the acid catalyst, which is here, that looks like these sort of gray bits, you add this purple material, and you end up with what looks like miniature frozen peas. And this worked reasonably well, and artemisinin came out at the end of our reactor, but it was a bit gooey and not very pure. And then we had quite a mad idea. We tried to do the reaction in a mixture of ethanol and water. I wanted to do it in vodka, but you need more ethanol, a high concentration of ethanol to dissolve the starting material. But the reason why it's mad is because with the singlet oxygen with the paired electrons, the rate at which the electrons unpair depends on the solvent, and everybody knows that water causes it to unpair very quickly. But it turned out, because our reactions were being done at a very concentrated solution, that actually the reaction went faster in ethanol and water than it did in either pure ethanol or in dichloromethane. So we got quite excited, and we repurposed our high-pressure reactor, so this time we could just flow ethanol, water, and oxygen up through it, and tried the experiment. And this was done again by Zach and two students, Sam Miller and Jess Bellamy. And it worked really well, but the most exciting thing was at the end, when we started to evaporate off the ethanol, and the Artemisinin precipitated completely pure. And we could take one crystal of this to the X-ray lab, which conveniently was next door to our lab, and they could get the crystal structure in only an hour and a half. It's a known crystal structure, but the material was pure enough to give a diffraction pattern straight away. And all the other things, the catalyst, and the solvent and everything else went through the filter. So you have the basis of quite an interesting process. You put in oxygen and the starting material, irradiate with light, distill off some of the solvent, filter off the product, and recycle everything else. And also, because you're using water and sulfuric acid is soluble in water, you can replace the toxic trifluoroacetic acid with sulfuric acid. Now, of course, I'm not suggesting you can drink sulfuric acid, but it is a lot less toxic than trifluoroacetic acid. So this is water, don't worry. Mike and I got quite excited, and we really wanted to broaden our project and try and take this idea of using photochemistry much more effectively into the chemical industry, or pharmaceutical industry at least. But it's a huge task, and we decided that research groups really need to combine together to get any effect. So Mike put together a team and launched a big project called Photoelectro. And Photoelectro involves Bristol University, Southampton, and Nottingham, and it involves both engineers and chemists. So there's photochemist Kevin Booker-Milburn in Bristol, two chemists in Southampton, Richard Brown, who's an electrochemist, hence the name Electro, and Dave Harrivan, who's an organic chemist, and then a mixture of engineers and chemists at Nottingham. And we have various aims, of which the one I'm only going to talk about is trying to design more user-friendly reactors. So I feel we need a demonstration. Chemistry lectures always need a demonstration. Let me explain. The problem with photochemistry is that if you want to promote a reaction by light, the light has to be absorbed by the solution. So if you have a colorless solution, you can shine a light straight through it. But if you want to do a photochemical reaction and take a colored solution, perhaps a bit more, should always put the top back on the reagent bottle. So, but now, if you put the light through it, it's absorbed. It doesn't even get near the middle. So, I need reinforcement. Cheers. It's nice wine. So, it's what you're going to get for dinner. So, what you have to do is to have thin films of liquid so that light can penetrate all the way through. So I just want to show you two approaches we've taken. The first one is using this sort of apparatus, which is called the rotovap, or colloquially, and our equipment is called the photovap. And the idea is that if you spin one of these with a colored liquid, you get a nice thin film of the colored liquid. So the photovap consists of just an ordinary rotary evaporator with some powerful lights here and two pumps, one to pump material in and the other one to pump out. So you pump in some material, your reaction mixture. The computer starts the rotary evaporator spinning, switches on the lights, does it for a short time so everything reacts, then switches off the lights, stops the rotation, pumps out the product, and you run the reaction as a semi-continuous reactor. And we're now collaborating with the company Ascent, and you can buy a sort of posh bank of lights to convert your rotary evaporator into a photoreactor. And with the right product, you can make 100 grams an hour in equipment just in your lab. 100 grams an hour is more than a kilo a day, and a ton a year is only 3 kilos a day. So you can start almost manufacturing it in your lab. The other reactor I want to tell you about is slightly more complicated. It's called the Vortex Reactor, and it involves essentially a glass tube, like a big test tube, with a stirrer in the middle, but the stirrer is very fat and completely smooth. And you flow material in here, solution in here, and it comes out at the top. But what happens is that when you spin this stirrer very fast, it creates little vortices that are called Taylor vortices, so the solution is all stirred up and goes next to the glass. And also at the same time, the solution scours the glass so that muck doesn't get deposited on the glass and stop the reaction. And light is shone from the outside to promote the reaction. And with our engineers at Nottingham, we've done CFD modeling, and you can see here's the modeling of the reactor, and this is the actual reactor where you can see the streams of bubbles. And this is not a simulation, this is a reactor actually running, and you can see these vortices, rather like rings, threaded onto the stirrer. And of course, we tried it with Artemisinin, and in our prototype for a small reactor, we can make about 5 grams a day, pumping the thing continuously, but now we've scaled it up to more than 200 grams a day. And our long-term vision is that we should end up with a sort of whole reactor pool of different photochemical, electrochemical, and thermal reactors, so that when you want to make a complicated molecule with multi-stage production, you can string them together in a little train, or daisy chain if you like, so that you can use it as a kit to make whatever chemical you want. And the reason why this is important is because the pharmaceutical industry is changing. And personally, personalized medicine, which is based on genomics, has made it clear that medicine that work for you may not work for you. So you need different medicines for different people to treat the same thing. So that means that you need to produce smaller quantities of many more different products. And so you need very agile manufacturing, and to do this, you need improved engineering. So our feeling is that together, that means not just our group, but with the wider engineering community, we can help realize the vision of making chemistry more sustainable and powered by light. So with my last slide, I just need to thank everybody. And I would like to thank all my students, co-workers, colleagues, collaborators. But particularly, I'd like to thank Mike George, who's my younger colleague, because without him, I would not have been able to continue my research as long as I have done. And Steve Howdell, my first student with supercritical fluids, who's now head of department. And I'd particularly like to thank Steve Pickering, who's our engineering collaborator in Nottingham, who's helped us develop the Vortex Reactor. Obviously, I should thank everybody who's funded the research, but I would like to end up by saying that we don't always recognize, as well as we should do, the role of technicians in supporting the scientific and engineering enterprise in the UK. And you will, if you look afterwards at the reception, you will see I'm wearing a badge saying, I love technicians. And truthfully, it's much easier for a university to get a new professor than it is to get a good new technician. You just pay the professor lots of money and the professor will come. But finding the technician is harder. And we have 3 outstanding technicians, Rich Wilson and Rich Meehan, who've made all the apparatus that I've talked about, and Mark Geiler, who I worked with for 35 years, who keeps the entire inorganic chemistry section at our university running. So thank you for your attention.